There we go. All right, so we will do test corrections tomorrow, like I said, and today we're going to talk about electromagnetic waves. Now, there's, depending on what you know from prior classes in science, if you've had this conversation, this content in middle school, perhaps, you might know a lot of the terminology, but for some of it, it may be brand new to you. So we'll cover it. You probably want to jot some things down in today's lesson with different terminology and different things that you'll need to know. All right, so Simon, you need to have your phone put away, please. So for electromagnetic waves, we often see them abbreviated EM. And the reason they're called electromagnetic is because it has both an electrical component and a magnetic component. And this is what it actually looks like in terms of representation of electric fields and magnetic fields. This is a little bit more, I'm not going to test you over this relationship, but I think just seeing what it looks like can maybe help you understand why they're called that way. In AP Physics 2, we actually learn about both of these kind of fields in quite a bit of great detail. And we learn a rule actually called the right hand rule, where you use your right hand, you point with your finger in one direction, your pointer finger, you point with your other fingers 90 degrees to that, and then you point with your thumb 90 degrees to that, so you actually see three things. And we use that to try to figure out which way these waves are moving and which way the magnetic part's going and which way the electrical part's going. So the details of this are beyond what you need to know for the class, and so I'm not going to test you over this, but I just thought you might be interested to see what it actually looks like in terms of, as light passes, it generates both an electric field and a magnetic field, and that's why we call it electromagnetic waves, because it has both fields that it's generating as it goes. And so I don't know if I showed you, well, I can show you kind of the connection between, let me grab a battery here, if I have any left. Let's see if I have some over here. I didn't think about showing you this before, but this would actually help you kind of see, I think, the connection between electricity and magnetism. Unbury a little bit here. We're gonna put it. No, I don't want to keep looking too long here. I thought I had it right on this shelf, but I must have put it somewhere else. So. All right, well, I'm not finding it right now, so I'll dig around for it, see if I can find it, and then show it to you next time tomorrow when we meet, because like I said, I don't want to wait too long here. Oh, there it is. I did find it. So this is just a metal bolt So hopefully I can hold it close enough to the camera so you guys can see it on the video. It's just a metal bolt, and I've wrapped some electrical wire around it. So I've got bare wire on this end and bare wire on this end. And if I touch the ends of that wire to the battery, this actually now has electricity flowing through the metal, or through the wire around the metal. Now the wire is insulated, but that electricity creates a magnetic field, so I can actually magnetize the bolt. But then when I disconnect the electricity, the magnetism's gone. So the electricity passing through this wire actually generates a magnetic field so that I can pick up objects with something that's not naturally magnetic and then take away the electricity and lose the magnetism. So that's kind of a visual of the connection between the two. All right. So the things that you do need to know though, electromagnetic waves are modeled a couple different ways. Sometimes they're modeled as waves, which we've been studying quite a bit here over the last few weeks, waves and simple harmonic motion. Sometimes they're modeled as particles. And so we'll talk about them in both ways, and we'll kind of divide up. Certain characteristics are easier to understand when we think about light traveling as particles. Other concepts are easier to understand when we think about light traveling as a wave. And so, like I said, we'll kind of go back and forth depending on what we're covering that suits our needs best. All right, so sometimes you'll hear this called the wave-particle duality of light, because it has properties that both exhibit wave properties and also that exhibit particle properties. All right. So the particle type of properties would be things like reflection. We know that light reflects off of mirrors and such. And so that particle model helps us understand reflection. But we also see some strange things about how light passes through openings that more matches waves. Like if you, at the ocean, if you see different breaks in the ocean, you see how the wave patterns change when it hits different reefs and different blocks. And we also see that with light. We can see light, actually, the waves change and create interesting patterns, and it behaves more like a wave in that sense than it does particles. Now, on the electromagnetic spectrum, there is a list of different kinds of energy, different kinds of light waves, but there's only a small portion that we can actually see, and this is what we usually call light. And you guys probably know an acronym for this sequence here of colors. You guys learned that acronym of going from this end to that end? Anybody heard it before? Red, orange, yellow, but there's like a RGB. Yeah, the RGB is the abbreviation for the three primary colors, but have you guys heard Roy G. Biv? Does that ring a bell at all? Sometimes you learn that in middle school. It's red, orange, yellow, that's the Roy. G for green, and then Biv is blue, indigo, and violet. And so that's the order that the visible light is. And the bigger value here, 750, means these have longer wavelengths. And the smaller value, 400, means these have shorter wavelengths. So our eyes can see wavelengths from 400 to about 750 nanometers. And this is nanometers, so nanometer is 1 × 10 to the -9. So these wavelengths are microscopic, they're really small. It's times 10 to the -9 meters. But when they're in this range, our eyes can actually see it. And when it gets just a little bit longer than red, we call that infrared. And you probably have heard of like infrared goggles. That's, in the military they use them so they can see in the dark, because they're not seeing the visible light, they're actually seeing infrared light, which is heat. There's heat coming off from living objects, and so if they use infrared goggles, they can see the heat coming from different things. And so then if you go longer yet, then there's microwaves. So your microwave oven actually works with these kinds of electromagnetic radiation waves, much longer. And also cell phones, the signal to the cell tower uses also microwaves. And then radio waves, when you listen to the radio in your car, that is very long wavelengths of energy, electromagnetic radiation. If we go a little bit smaller than the blue light, the violet, we get to ultraviolet. And so that's what gives us sunburn, that kind of radiation from the sun, UV rays, or you might have seen a black light, which gives UV light. And it's ultraviolet. We can't really see it exactly because it's just beyond what our eyes can interpret, but we can feel it. It burns our skin if we're in it too long, if we're exposed to it too long. And then if we get to even smaller wavelengths, we get to X-rays, which are literally what they use to take an X-ray of your body when you have a broken bone or they think you might have a broken bone. And then when they get even smaller, we get to the range where they're called gamma rays. And gamma rays are the smallest, and they actually use that kind of wavelength in different kinds of surgeries, or also different kinds of other scanning techniques beyond X-rays in the medical field. So all kinds of different wavelengths, that all of these kinds of energies, all of these kinds of waves are called electromagnetic waves. They have both an electrical part and a magnetic part, but we can only see that very small portion right in the middle, the visible spectrum. All the rest we can use. When we use microwaves, we listen to the radio, and we use infrared and ultraviolet, we use all these things, but we can only see them if they're in that visible span, that very small little increment. Now, one thing that you need to know, in addition to the order here, the Roy G. Biv, so red, orange, yellow, green, blue, indigo, violet. That's the Roy is the red, orange, yellow, G for green, and then Biv, blue, indigo, violet. As we go down the spectrum this way, we're getting from long wavelengths to short wavelengths, and the energy is the opposite direction. So going this way, the wavelengths get shorter and the energy gets greater. Going this way, the waves get longer and the energy gets less. Okay, so radio waves don't have a lot of energy, but they do have very long wavelengths. Gamma rays have a bunch of energy, but very tiny wavelengths. Okay, so understanding the difference between where its wavelengths are bigger and where its energy is bigger is important to know for the spectrum. All right, so here's just another view of the visible light, and from 400 to 700, 750 is all that our eyes can interpret. Everything above or below, everything that's smaller or larger than that, we can't see with our human eyes. All right, now I want to give you a couple key points here, and then we're going to watch a short video that goes over some of these different kinds of waves and how they're used. All of them, so all of these that we looked at here, from gamma to radio, they all travel at the speed of light. And we use the variable lowercase c to represent the speed of light. Now, that's not 100% true. They all travel that fast through a vacuum. But we don't live in a vacuum, so they all travel that fast almost through air. It's just barely slower than the speed of light through air. Now, if it's traveling through other media like water or glass, then it's going to actually travel slower. But all of these waves travel through a vacuum at the speed of light, and through air just ever so slightly less than the speed of light. So it doesn't matter whether it's radio, microwave, visible, they all travel at the same speed. And so, like I said, in a vacuum, that value for the speed of light, it's 186,000 miles per second, but we don't really use miles and seconds. I just wanted to give you that so you could kind of reference how big it is, how fast it's moving. 186,000 miles every second. In meters per second, which is what we actually need the value for our calculations, it's 3 times 10 to the 8th meters per second. So light can go around the world 8 times every second. Right? So let's take a look at this video that's going to give you some more detail about the different kinds of wavelengths of light. might have to switch the sound. I gotta get to a place where I'm. There we go. So we
Something surrounds you, bombards you, some of which you can't see, touch, or even feel. Every day, everywhere you go, it is odorless and tasteless. Yet you use it and depend on it every hour of every day. Without it, the world you know could not exist. What is it? Electromagnetic radiation. These waves spread across a spectrum from very short gamma rays to X-rays, ultraviolet rays, visible light waves, even longer infrared waves, microwaves, to radio waves which can measure longer than a mountain range. This spectrum is the foundation of the information age and of our modern world. Your radio, remote control, text message, television, microwave oven, even a doctor's X-ray, all depend on waves within the electromagnetic spectrum. Electromagnetic waves, or EM waves, are similar to ocean waves in that both are energy waves. They transmit energy. EM waves are produced by the vibration of charged particles and have electrical and magnetic properties. But unlike ocean waves that require water, EM waves travel through the vacuum of space at the constant speed of light. EM waves have crests and troughs like ocean waves. The distance between crests is the wavelength. While some EM wavelengths are very long and are measured in meters, many are tiny and are measured in billionths of a meter, nanometers. The number of these crests that pass a given point within 1 second is described as the frequency of the wave. One wave, or cycle, per second is called a hertz. Long EM waves, such as radio waves, have the lowest frequency and carry less energy. Adding energy increases the frequency of the wave and makes the wavelength shorter. Gamma rays are the shortest, highest energy waves in the spectrum. So, as you sit watching TV, not only are there visible light waves from the TV striking your eyes, but also radio waves transmitting from a nearby station, and microwaves carrying cell phone calls and text messages, and waves from your neighbor's Wi-Fi, and GPS units in the cars driving by. There is a chaos of waves from all across the spectrum passing through your room right now. With all these waves around you, how can you possibly watch your TV show? Similar to tuning a radio to a specific radio station, our eyes are tuned to a specific region of the EM spectrum and can detect energy with wavelengths from 400 to 700 nanometers, the visible light region of the spectrum. Objects appear to have color because EM waves interact with their molecules. Some wavelengths in the visible spectrum are reflected and other wavelengths are absorbed. This leaf looks green because EM waves interact with the chlorophyll molecules. Waves between 492 and 577 nanometers in length are reflected, and our eye interprets this as the leaf being green. Our eyes see the leaf as green, but cannot tell us anything about how the leaf reflects ultraviolet, microwave, or infrared waves. To learn more about the world around us, scientists and engineers have devised ways to enable us to see beyond that sliver of the EM spectrum called visible light. Data from multiple wavelengths help scientists study all kinds of amazing phenomena on Earth, from seasonal change to specific habitats. Everything around us emits, reflects, and absorbs EM radiation differently based on its composition. A graph showing these interactions across a region of the EM spectrum is called a spectral signature. Characteristic patterns, like fingerprints within the spectra, allow astronomers to identify an object's chemical composition and to determine such physical properties as temperature and density. NASA's Spitzer Space Telescope observed the presence of water and organic molecules in a galaxy 3.2 billion light-years away. Viewing our Sun in multiple wavelengths with the SOHO satellite allows scientists to study and understand sunspots that are associated with solar flares and eruptions harmful to satellites, astronauts, and communications here on Earth. We are constantly learning more about our world and universe by taking advantage of the unique information contained in the different waves across the EM spectrum.
All right, So there.
Found the single biggest productivity hack of 2021. It's this Google Chrome extension called Speechify, and it literally does my read.
All right. So again, if we look at the spectrum, here's just I like this one because it shows you the same thing as before in terms of the relative small range that our eyes can see. It's just this tiny little sliver. That's all our eyes can see. And the length of those waves that our eyes interpret are around the size of a bacteria or a virus. They're really tiny waves. And then as we get to X-rays and gamma rays, they get smaller and smaller down to like atoms and molecules. But as we go the other direction into infrared, they're more like the size of a cell. Microwaves are more like the size of this period, or like it showed on the video, the size of a die, like a dice that you roll. And then we get to radio waves. They can be anywhere from a baseball to soccer fields to mountain ranges. So the radio waves, depending on what we're using them for. If they're radio waves for literal radio tuning, listening to the radio, that's within a given spectrum, depending on whether it's AM or FM. So you tune into the correct frequency to pick up the station you want. But then there's other radio waves that we might send out for like long range interpretation of what's happening on other planets that would have even longer wavelengths. All right, so it's important to understand what these are, these different branches or different kinds of electromagnetic radiation, to know which ones are longer, which ones are shorter, which ones have more energy, and which ones have less energy. Okay, those are kind of the details that you'll need to commit to memory. All right, now we've talked about this before, but just a quick reminder, just like with sound waves, just like with other waves that we've studied, mathematically, we talk about the same aspects, the crests, the troughs, the hills and valleys. We talk about the distance between one spot on the wave to another as being the wavelength. We talk about the height of the wave being the amplitude. We talk about how fast the wave is moving past a certain point as the frequency, and how long it takes for a certain wave to go by as the period. We use all those same terminologies, but we're also going to sometimes see these new words, nodes and antinodes. The antinodes are the crests, and the nodes are where it crosses the equilibrium line. And we won't come back to that too often, but you might just see it in passing. I'm not going to actually test you over those words, those two, but you might see them in passing as we describe. So if you see antinode, it's referring to that peak part of the wave, and the node is where it's at zero, where it's crossing that equilibrium line. Now, a few things you need to know. One is that they do not, these electromagnetic waves, all of the types, do not require a medium to travel through. So they can go through space. They can go through a vacuum. So like we saw with sound, when I showed you the video of that alarm that was in the vacuum, as they sucked the air out, you couldn't hear the alarm anymore because sound needs some sort of medium to travel through. Light can go right through that vacuum, whether it's visible light or any of those other kinds of electromagnetic radiation. That's why it can go through space. We can send radio waves, we can see the ultraviolet light, or we can not see, but feel the ultraviolet light and the infrared radiation from the sun as warmth, but because it can travel through space. And like we saw on a previous slide, all of them in a vacuum travel at 3 × 10⁸ meters per second. So you probably already have that number down. That was on a previous one. Another thing that's true about all of these different kinds of waves is they can both be reflected and they can also be refracted. Okay, so if they're reflected, they're bouncing off some surface. If they're refracted, they're actually changing their angle as they go through a different surface. So that refraction principle is why when you see something in the water, it looks like it's in one place, but then when you reach in to grab it, it's actually in a different place than you think. So if you've ever been spearfishing where you're above the water, like you can do spearfishing where you're diving, but if you do spearfishing, or in the South, a lot of places people do gigging, where they're like wading through shallow water and trying to gig fish or gig frogs or something like that with a spear. You can't aim where it looks like they are because the light travels through the water at a different speed than it travels through the air. So when it hits the water, it bends. And so it looks like it's further away from you than it is. It's actually closer than it is. So when it's reflected, it bounces off. When it's refracted, it changes its speed and bends. We'll dig into those terms more as we get further along. But all of them, radio waves, microwaves, gamma rays, all of those different kinds of electromagnetic radiation can do both, or will do both. They can also all be either emitted or absorbed. So we see them emitted from a radio tower or a microwave wave for cell phone towers. We feel the heat from an infrared light keeping the food warm at a fast food joint, or the heat coming off of a fire. Those would all be ways that different kinds of electromagnetic waves come out of something, they're emitted from something, but then they can also be absorbed. So when a signal comes down from a satellite, we can use an antenna to absorb that electromagnetic radiation and then interpret it. Our bodies can absorb that infrared radiation and warm up. Our bodies can absorb that ultraviolet radiation and get sunburned. So you can have things that emit these waves. You can also see these things being absorbed. And then the wave equation that we learned in the last unit also applies to these kinds of waves. So we learned that the speed of the wave is equal to the frequency times the wavelength. And that's also true for all of these different ones.
What was number 5?
They can be emitted or absorbed.
Okay.
All right, so you should have this equation in your last unit because we used it on your recent test. But now we're going to apply it to electromagnetic waves as well, not just sound waves, not just other mechanical waves. And just like before, we'll still measure the speed in meters per second, we'll still measure the frequency in hertz, and we'll still measure the wavelength in meters. So all those units still need to be the standards. So let's have you practice a problem using this equation that you're somewhat familiar with. We've used it before, but now with numbers that would match light. So using your calculator, let's see if you can figure out this question. It says the middle of the visible spectrum is green. It's the G in the Roy G Biv, right? So it's right in the middle of what our eyes can see. They want you to figure out, well, what is the wavelength of green light if the frequency is 5.5 times 10 to the 14th hertz? So they're giving you the frequency. They want you to find the wavelength. And because it's light, the speed is the same. The speed is the speed of light down here. Okay, so see if you can calculate the wavelength. So you got an answer, raise your hand so I can kind of see time-wise how much you need. All right, who's got an answer for us? What are you coming up with?
I did it wrong.
You did?
I think it's a really small number.
Okay, that's probably right then. It should be really small. What'd you get?
5.45 -7.
Okay, so about 5.5 times 10 to the -7th. So it is really small. Remember, our eyes can only see from 400 to 700, not meters, but nanometers. So if we think about what this is to make it a little bit more relevant to our imagining of how big something is. So 5.5 times 10 to the -7th meters is about 0.00055 millimeters. So if you think about the size of a millimeter on a ruler, the millimeters are these small markings, right? So actually that's inches. So it's these small markings on this side. So if it's millimeters and it's 0.00055 of these, they have to be pretty tiny, right? And so The way they're usually represented, it's fine to write your answer this way, 5.5 times 10 to the negative 7th meters, but usually we'll see them written as nanometers. And nano means times 10 to the negative 9. So when you see that 5.5 times 10 to the negative 7, you'll usually see it rewritten as 550 nanometers. All right, so thinking back to the spectrum that we saw before, that 550 is right in here, just like we would predict. It's that shade of green. All right, waves and rays, a couple new things about waves. With light waves, they actually demonstrate something similar to water waves called the Huygens principle. And I don't speak Dutch, so I'm not exactly sure if that's how you pronounce it. I've heard some of my professors in the past call it Huygens. I've heard some say Huygens. I don't know if any of you speak Dutch or know how that would be pronounced, but it's Christian Huygens is the guy's name that came up with this principle. And his idea is that each point on a wave acts as a source for new waves when it hits a boundary. And so when it hits a boundary, it's going to behave like water waves. When water waves hit a reef, when water waves hit a sandbar, when water waves hit a big pile of rocks or a small island, the waves change and bend and change direction. Well, light waves do that as well. And so if you think about every point of the wave as being able to generate a new wave, it helps you kind of picture what he means here. So this diagram shows that we've got this initial wavefront, which is the black line on the left, and it's moving in the direction of the blue arrows. But if it hits a boundary, every single point that we could imagine, so they're just showing 5 blue points represented by the arrows, every single one of those points could generate a wave reflecting off. And it's not just those 5 points, it's an infinite number of points. But the principle behind his idea is that if all of those little points can generate their own waves, when light or other waves hit a barrier, it makes sense. Some of them are going to go this way, some of them are going to go that way. They're going to take different directions, different angles, and that's going to create what we call interference. And we've talked a little bit about interference with sound canceling headphones, how you have that destructive interference, it cancels. You can also have constructive that helps you build louder. So I'm going to skip over this one because it's not a major principle, but this next part I do want to make sure you understand because you do need to understand illumination. And we're talking about illumination in a literal physics sense here, not in a metaphorical way, but we measure the illumination of light in what's called lumens. And so if you've looked at light bulbs, if you've bought light bulbs before, especially with the different LED and different other kinds of light bulbs, not the older incandescent ones, they'll almost always tell you what their lumens are, which is how bright. And then they'll also talk to you about the wattage, which would be the energy that they take. And so generally nowadays, they're trying to make light bulbs that use a very little amount of wattage, so they don't need much energy, but they still create a lot of lumens. They still create a lot of brightness. Now, the brightness of light depends on how close you are to the source. So you can see here that if you are 1 meter from the source, if it's like a projector putting something onto a screen, 1 meter away is going to have a certain amount of brightness. But then if you go another meter away, it spreads out that light to 1/4 the brightness. And then if you go another meter away, now you're 3 meters away, it spreads out the light to 1/9 of the brightness. So it keeps getting diminished less and less and less. So if 1 meter is a certain lumens of brightness, 2 meter is going to be 1/2 squared. It's going to be 1/4 as bright. If you're 3 meters away, it's going to be 1/3 squared. It's going to be 1/9 as bright. So this works like sound waves. It's an inverse square rule, like we had on the test this last time, where if you double the distance of the sound source, it gets a fourth as loud. And if you double the distance on a light source, it gets a fourth as bright. So it's that same sort of reciprocal inverse square rule. And it allows us to predict how bright a light will be based on the distance. So if you're a projectionist, if you're working for a company that's trying to use different projection systems, you need to know how far away can we put this projector so that we still get enough light to be able to see it. Any of you guys have like projectors that you use at your home for TV or anything like that? Some of you? When our last TV died, we just got a projector because it was cheaper than a TV, and we can make it like fill the whole wall. And so, but when we were doing that, if we want to watch TV during the day, if it's too far away, it's not bright enough to see unless we close all the windows and put shades and stuff. So we keep it kind of at a distance where it doesn't fill the whole wall. It's probably about the size of this screen, but it's bright enough because it's close enough that we can still see it during the day without having to close the whole house down. So, all right, couple of videos. I think we just have time for one here. We'll just watch one on this brightness and watts. It's 11:10, right? Yeah. Okay, I think there's one that's only like a minute and a half, unless I'm mixing it up with a different video. Yeah, this one.
Lumens is the new watts. Watts is so passé. Lumens is the new terminology to use when picking out a new energy efficient, the amount of energy required to power a light bulb. This is much more important to consider when deciding between a huge variety of light bulb options that use far less energy now than they used to. Their wattages are significantly lower and rather insignificant to compare. For example, the light of a typical 60-watt incandescent bulb, about 800 lumens of light, can be replicated with just one 15-watt CFL bulb. This means that CFLs use only 25% of the energy to achieve the same results as typical incandescent bulbs, which equals a significant energy savings over time. Not to mention, they can last about 10 times as long too. LEDs use just 15% of the energy as typical incandescent bulbs and last about 25 times as long, resulting in even greater savings. Now, labels on light bulb packages clearly identify the number of lumens, the estimated yearly cost of the energy needed to light the bulb's estimated lifespan, the approximate light appearance as it compares to traditional incandescent bulbs, and the amount of energy used. Don't be left in the dark when it comes to choosing your new light bulbs.
I hope you have a good rest of your Monday.